Hello, welcome back. Today we're going to continue our discussion on limits. We're going to specifically talk about graphical limits and algebraically, and solving them, start talking about them algebraically. Now, the first three questions are kind of a warm-up, so if you want to pause the video and just try the first three questions and unpause it, and we'll go over the answers, which I'm about to do right now. So, we are given two limits, f of x and g of x, and in both cases they're both approaching a. Now from yesterday you should remember, if we're looking at the function f of x, as we're approaching some x equals a, on both sides, the left side and the right side, the value here tells us we're approaching some value of 2. Now it could be filled in, it could not be filled in, we don't really know anything. G is kind of the same way. As we approach a from both the left side and the right side, for g of x we're approaching 3. Now for the most part we can treat a limit just like a value. So in other words, we can treat them algebraically. I can add them together, I could subtract limits, and we're going to talk a lot more about that in another video when we start talking more about the properties of limits. But for now it's pretty easy. So if we look at a question like number 1 right here, this says take the limit of as x approaches a of 5 times f of x. So all this is doing is it's just saying, hey, I'm going to take that limit of f, which is 2, and multiply it by 5. Now there is a special format for the AP. You should write this out. Rewrite it, the limit as x approaches a of f of x. I know it seems kind of weird to do that because you can do all of this in your head, but the AP does want a specific format for us. So I can write this as 5 times, well, f of x is just approaching 2, so 5 times 2, it's just 10. And there's our answer. Same thing for part number 2. We're going to split this up. We're going to take 6 times plus g of x. But when I write it, I'm going to write this as the limit as x approaches a of 6 plus the limit as x approaches a of g of x over the limit as x approaches a of f of x. Alright, so let's see how we do this one. Well, this first one right here, this limit as x approaches a of 6, that's just what we call a constant. This is like the line y equals 6. And if you think of the line y equals 6, it's just a horizontal line. Even at the value of a, my value is still just going to be 6. So this just becomes 6 plus, we know what g of x approaches, it's 3, and we know f of x approaches 2. So I can leave it like this, I'm cool with that. Or if you want to simplify it, whoops, I hit my eraser, and that becomes 9/2, or 9/2. Likewise, for part 3, if I'm going to square them, we would get the limit as x approaches a of f of x squared over the limit as x approaches a of g of x minus the limit as x approaches a of 2. So this is just squared. I'm just going to do that in my work up here, ran out of room here. This just becomes f squared, so it just becomes 4 over, we know g is just 3, and this is our constant rule, so minus 2. That's our constant. And if we simplify that, we just get the number 4. And there's our answers. Very easy to do. All right, so let's take a look at some more graphical limits. Okay, we mentioned these a little bit yesterday. And we just want to say here. Now, yesterday, you might recall, we talked about a very big difference. That there is a difference between what we call a value and a function. So if we look at number 1 right here, there is no limit right here. Sorry, the limit and a value, sorry. This is a value. In other words, I want to know what is the value of the function at -3. Remember, we talked about yesterday, the word value, we're at that point. And I can get that pretty easy. At -3, it looks like the value is 0. Now, question number 2 says, well, what are we now approaching? That's what that limit says. Now, what are we approaching? But you got to be careful. That little minus sign up there, you might recall from yesterday, means we're approaching from the left side of the function. So at -3, if I'm approaching from here, if I draw like a little line right here, there's the left side. As I'm approaching from the left, my values are approaching 0. And for the next one, same thing. But this one says now I'm approaching from the right side. So now if I look over here, here's the right side. I'm approaching from the right. My values are also getting closer to 0. Remember, we talked about yesterday like the limit being like a road. You're walking on a road. And you're approaching this house. Like you and a friend are approaching the same house. One's approaching from the left and you're approaching from the right. But you're approaching the same value. Whoops, I don't want that to go over there. That needs to be a 0. Now the next question, it looks the same. Like you have that -3, the -3. But if you notice, it doesn't have a plus or minus. You might recall yesterday, this is called the actual limit itself. And what we're looking at is, does the left equal the right? Am I approaching from the left the same as if I'm approaching from the right? And if we take a look here, on the left we're approaching from 0, and on the right we're approaching 0. So this would have an actual limit of 0, because the left and the right are the same. And that's what you really want. What you really, really want. So let's try for -5. Well, for -5, well, here we are approaching again. That's our left. And we're approaching from the left. Our values, if you notice, not the value is, but my values are getting closer to what? In this case, -1. Over here, here's the right side. On the right side, as we approach -5, our values are approaching 0. Now, if you notice, and now we're looking for the actual limit for part 7. So for this one right here, the actual limit, if we notice, the left is approaching -1, but the right is approaching, is approaching 0. So they're not the same. So we're going to say that this does not exist. D-N-E, Denis, my old high school girlfriend, Denis. All right. So now, but we're going to justify why. And we actually have to do this on the AP. They'll say, explain why. Because, and we'll nerd this up a little bit, the limit as x approaches -5 from the left of our function does not equal the limit as x approaches -5 from the right of our function. Notice, you have to have this notation. Okay? That's limit notation right there. Okay, so you need something like that. So here the limit does not exist because we're approaching different areas. It's like you and your friend, ready? Your friend's approaching this house at -1 street, and you're approaching this house at 0 street. You're not approaching the same value, so therefore we say that the limit there actually does not exist. It's kind of like this. Two roads crossing it. You're driving along the road. One road, right? They're not going to meet. The limit there does not exist. You want them to become the same right there. All right, now, of course, number 8, that's our value. The value at -5, be careful. That's a hole, dear Eliza, a hole. You're looking for this point. It's -1. That's the value. Now, if you notice, look at the example up here. The value, whoops, we said the value there was at -3 was 0. That just got erased there. Notice here the value and the limit were the same. That's ideally what you want. Over here, the value and the limit are not the same. They don't always have to be the same. The value, you don't always have to approach what your value is going to be. And that's a really interesting thing that happens in calculus. Now, we talked a little bit, yes, about this idea of continuity. And then the next part says, is f continuous at -5? Now, we're going to go into a much more formal definition later on. We just want to know if it's continuous. And the real simple idea is, at -5, is the value the same as the limit? And in this case, the answer is no. And for now, we're just going to say this, that the value does not equal the limit at x equals -5. Now, later on, this will not be accepted on the AP, but later on this unit, we're going to talk about a much more formal definition of continuity, or something being continuous. Now, what about -3? Yeah. The value was 0 and the limit is 0. So yes. And again, we're just going to shortcut it right now because the value equals the limit. This is a very important role for us in terms of continuity. It says, like, if you're driving down a road, you're going to hit every point on that road. This one says you have a few potholes. That's a funny joke later on. What about at -2? Is the function continuous at -2? Well, we can look at it. At -2, well, let's just see the limit. the limit as x approaches negative 2. Let's see what that equals. From the left, we're approaching negative 1, and from the right, we're approaching negative 1. So my limit is going to be negative 1. But what about the value at negative 2? See, there's a hole there. The value is negative 2. So let's think about that. I have my limit, what I'm approaching, and I have my value, what I want it, what it's going to actually equal. So in this case right here, they're not the same. So the answer would be no. And we're going to say the reason for now, value does not equal the limit. For now, when we get to later on this unit, we're going to talk about a much more formal definition. So let's take a look at the graph. Now this graph isn't right here for us, so I got to kind of do something like right here. Something like this. I think it looks something like this on your paper. Okay, there we go. Let's just make that up. All right, so try this one. Pause for a second and just see if you can try this one, and I'm going to go ahead and continue. So for the first question, it says, what's the limit as x approaches 2? Whoops. There we go. Not to scale. My favorite phrase. So as we approach 2, and let's, I guess we can, we'll just make this a 1, 2. So we can make the scale whatever we want. As we approach 2 from the left, it looks like it's approaching 2. As we approach 2 from the, remember this is my right side, that's my left side, it also looks like it's approaching 2. What's the actual limit at 2? It's 2. My value is approaching 2. What's the value at 2? 2. So take a look here. The limit is 2 and the value is 2. Well, what could you tell me about continuity here? Would this be continuous? And the answer is, of course, yes. This would be a continuous. Oops, sorry. The value. Oh no, I messed up. There we go. I think the value is up there. So the value was at, like, let's say 4. Whoop, let me put that back up here. There we go. We'll put that value at 4. There we go. Sorry about that. So in this case right here, the limit was 2 and the value was 4. Sorry, I'm looking right at my notes, believe it or not. So in this case right here, the value and the limit are not the same, so this would not be continuous. Okay. Part E says a fun one. It says find the values of C. Anytime you see the letter C right here, they're talking X values. You might be saying, why will it be C? Well, C is something we literally use as a number, where X is just a variable. So they're looking for all the X values for where the limit will exist. In other words, everywhere that the left will equal the right. That's all we're looking at today. That the left equals the right. So take a look here. At this point right here, if I pick a point here, in my line of the line, yep, from the left and the right, it's always the same. And matter of fact, that actually occurs everywhere. Even at this hole right here. Even at the hole. From the left and the right, I'm approaching the same value. It's just that as soon as I reach that value, I jump to here. Remember, limits don't really have anything to do with the value of a function. There's some crazy limit. You can draw functions with an infinite number of holes in terms of values, but it'll still have limits. It's crazy. We can do crazy things with these. So in this case right here, there is nothing here that's going to prevent the limit from existing. So we would say the x values is going to go from negative infinity to positive infinity. And that's it. All right. So go on to video number 2, and we'll take a look at some more problems.